This is Lisa Van Ness, and this is my Physics 2211 Lab 1 on constant velocity. So the purpose of this lab is to observe and analyze an object moving at constant velocity without changing directions. I use the online tools GlowScript and Tracker to create a computational and physical observation of the movement of the whiteboard marker. The results show that the change in position over time has a positive linear relationship, which indicates that velocity remained constant. So the main concepts we can see in the lab are Newton's first and second law. Newton's first law says that an object at rest remains at rest, and an object in motion remains in motion unless acted on by an outside force. Since there's no outside force acting on the whiteboard marker in theory, or at least in the computational model, the moving marker will remain in motion. And Newton's second law says that an object's net force is determined by its mass and the change in its velocity over a period of time, or force equals mass times acceleration. And since velocity is constant, net force should be zero, which supports the idea that the moving marker will remain in motion. External forces, though, such as air resistance and friction, can affect the velocity of an object. So the computational model didn't account for this, and there might be some discrepancies that will exist between the computational and physical data. So the experiment was to roll a whiteboard marker across a flat table in one direction. The initial conditions of the marker and the system and surroundings of the lab are defined on the left. And the tracker that I used was meant to establish an axis and track the center of mass or the marker over a specific time frame. And it showed the whiteboard marker moving from left to right, which is in the positive x direction. So here's our physical model. You can see a screenshot of us rolling the whiteboard marker on the left. Using the tracker, we were able to create graphs of the x and y position of the marker over time. As you can see in the x position versus time graph, the slope or the velocity is very linear, so indicating that velocity is constant. You can see our raw data on the right. Here is the coding I used to create the computational model. The things that I changed were the initial position of the marker as well as its velocity, and I found the velocity by taking two data points and finding the change in position over change in time. I also changed delta t to be 0.033 seconds, and I changed net force to be 0. So here is the computational versus experimental data. As you can see, the graphs are relatively similar, but not perfectly aligned. Again, this could be due to some external forces such as air resistance and friction acting on the physical whiteboard marker, which would not have been reflected in the computational data. So what if the axis was different? The graph that we have now has a positive linear relationship because the marker was rolled from left to right, which moves in the positive x direction. However, if we flipped the x-axis so that the marker was rolling in the negative direction, the graph would take on a slope of equal magnitude but opposite direction, or in other words, the velocity would become negative. The velocity would still be constant though, so the graph would continue to look like a straight line. So in conclusion, the predicted and observed models of the change in position over time were similar, and both graphs are linear, indicating that velocity is constant and that there is no net force, thus proving Newton's first and second laws to be true.